All right, I've mentioned continuity several times now. Let's define what we mean by continuous. First, we start with continuous at a point. A function's continuous at a point. The naive definition of continuous is you can draw the function without lifting up your pencil. So you've got some kind of graph here. And at this spot right there, I just drew it smoothly. I didn't have to pick up my pencil. I didn't have to do anything like go here and stop and then start again. That would be what we call a jump discontinuity. Or I didn't have to stop, leave a little open circle, and then start over. Or I didn't have to have a vertical asymptote, skip over it, and start again. So continuous means the function just keeps going through that point, and you didn't have to stop. That's actually not a great mathematical definition of continuity. So here is the mathy definition. A function's continuous at a point A if all three of these conditions are met, and it has to be all three. First of all, the function is defined there. So this guy's out. You can't have a hole. Secondly, the limits has to exist at that point. So this guy would still have a limit there, but he fails the first condition. And then third, those two have to be the same thing. The limit and the function value have to be the same. Three conditions to be continuous. The function has to exist. It has to be defined. The limit has to exist, and the limit has to be the same as the function value. Okay. We've played with this guy a couple of times now. We know that he really is x plus 2 as long as x does not equal 2. His graph just looks like this, except right here at 2, 4, there's a hole in the graph. This guy is not continuous at only at that one spot at x equals 2. He has what's called a hole, or sometimes called a gap discontinuity. Okay. What about this guy? Is he continuous at 3? Well, to check that, we need to check, does the limit exist at 3? When do limits exist? When both one-sided limits exist. So I need to check. We could check all this by graphing also. You could easily just graph this and check, but it's easier to do algebraically. I want to check the limit as x approaches 3 from the left. That means smaller. That means right there, what I wrote means using x as less than 3. A little bit less than 3. That means using the top formula. So that'll be what? -9 plus 4. That's -5. Now, let's check the other side. The limit as x approaches 3 from the right of f of x. So that means what I wrote right there means I'm supposed to be using x as a little bit bigger than 3. So I use this bottom formula. Okay, so he's a polynomial. I just plug him in. Let's see, that's going to be 12 minus 8. I think we get 4. The one-sided limits do not agree. That means the limit as x approaches 3, just in general, no left or right, does not exist. The function exists there, f of 3 exists. I'm allowed to plug in 3 here. In fact, it's this top one. It's just -5. That's where the solid dot is. This is where the solid dot is. That's an ugly 3, but that's a 3. The function exists there. The limit doesn't. It's not continuous. For a function to be continuous, function has to exist, limit has to exist, and those two need to be the same number. When does the limit exist? When both one-sided limits exist and are the same. Let's look at this guy. So this is a piecewise function where they filled in the hole. I'm not allowed to plug in 0 here, but somebody went and took that graph and they plugged in that one single point and said, when x equals 0, we're just going to make it 1. Did that hole that we plugged in fill it in right? See, it could be that the graph looks something, maybe it looked like this, where there was a hole there, and then somebody came along and said, well, I'm going to put the dot right there. This would not be continuous because the hole's not where it should be. The limit would be here, the function value would be here. That's not what happens in this case. Oops. I know, because we proved it in the last video, geometrically, the limit as x approaches 0 of sine of x over x is 1. So 3 things are happening here. F of 0 is 1, right there. Function exists at 0. That's step 1. I'm allowed to plug in 0. Step 2, the limit exists. We proved it before. Step 3, we got the same number. That means this guy had a hole in it and somebody came along and plugged that hole correctly where it should be. This function is continuous. At x equals 0. That's all we were asked about, was at x equals 0. Any function that you can write down in one single line is continuous on its domain. I'm going to write that down here. Write this in your note. Any function that you can write in a single line on its domain that's important. So what do I mean by write in a single line? I mean, not these piecewise ones. See, that took me 3 lines to write that out. Those you always got to check. Are they continuous? By checking all the one-sided limits. These you got to do some work on. You got to check. But if somebody hands you a formula where it's just one single line, there's no piecewise definedness to it, then you're guaranteed it's continuous everywhere in its domain. Numbers that are not in the domain fail the first condition. So here I've got a function written down in one single line. By the way, that's a really hard theorem to prove. We're not going to try to prove that. This is written in one single line. It's continuous everywhere that it's defined. Where is it not defined at x equals 5? The domain is -∞ to 5 union 5 to infinity. It's continuous at all of those numbers. It's not continuous at x equals 5. It's got an asymptote there. Okay. What about this guy? That's a polynomial. Polynomials, the domain's all real numbers. So when I say it's continuous on its domain, that's everywhere. I'm done. I don't have any work to do. All polynomials are continuous everywhere. This is continuous for all x's negative infinity to infinity. Okay, so the types of discontinuities we can have a hole with a removable discontinuity, also called a hole. We can have a jump or a gap discontinuity where somebody was drawing the graph and they picked up their pencil and moved it and started over again someplace else. There's a big jump there. Or you can have an asymptote of an infinite discontinuity. In this case, the limit exists and the function exists. They just don't agree. This one fails to meet that third condition. The function value exists because there is a solid dot somewhere. The limit exists because both one-sided limits exist and agree. It's not continuous because those are not the same value. Here, the function value exists. It's right there, whatever that y value is. The left-handed limit is this value. The right-handed limit would be this value. Those are not the same, so the limit does not exist. If the limit doesn't exist, you're not continuous. Here, the limit doesn't even exist. Oh, but it's infinity. Infinity is not a real limit. We've been lying to you with these infinities. That's not a real limit. That limit does not exist. We might write down, I might look at this and say the limit as x approaches a from the left of f of x is infinity. But that's not a real limit. For continuity, it has to be a real limit, a finite limit. So the limit here does not exist, and the function value does not exist. F of a does not exist. That's really ugly, eh? So this guy just fails on all the counts. The function doesn't exist. The limit doesn't exist. There's no way those things can be equal. Okay, let's take a quick look at this problem. Okay, where's all the places? We're assuming here that this guy goes on and on. So I'm not worried about what happens out here. Where's the functions discontinuous, and we'll classify those. Okay. And it's not really obvious to me what's happening here. I think this is implying that we've got a vertical asymptote right there. So this is a discontinuity right here. So at x equals -1, that's what we call a jump discontinuity. Here at x equals 0, we've got an infinite discontinuity. Because we've got this vertical asymptote. And then here at x equals 1, there's another discontinuity. X equals 1, we've got a hole. And we just explained why this one, I guess I'll explain it again in words. This guy doesn't exist because the limit doesn't even exist. This guy is discontinuous because the function doesn't even exist. There's no function value. In this one, the limit exists. The limit is 1. Both sides have gone toward 1. The function value, the function's defined. F of x or f of 1 is 2. But those don't agree. So the function's discontinuous there. Okay, we can have continuity from the left, from the right. We're really not going to do much with this. I'm just pointing out that they exist. You can have functions that you might say is continuous from the left or from the right. Meaning, if you have a picture like this, we could say if we wanted to, this guy is continuous from the right because the solid dot is on the right side. So if I'm only looking here, I'm coming, and I said all that backwards, I apologize. This guy's continuous from the left because on the left-hand side here, if I'm coming in from the left, I hit the solid dot. If this solid dot were down here and now we're coming in from the right, we would say continuous from the right. Continuous functions are continuous from the left and the right. If you've got a jump discontinuity, the side that has the solid dot on it, if either, is the one that gets the continuous from a particular direction. Okay, and then last thing today, the intermediate value theorem. The intermediate value theorem, you probably learned back in pre-calc. And it says if you've got yourself a continuous function on a bounded interval, then you're going to hit every point, every y value in between your lowest and your highest. That's what that says. So you know the y value at the start of your interval. You know this guy's y value. And you know this guy's y value. You pick some other y value that lives in between there. There must be an x value in your interval so that you hit that y value. It's what this really says is it's impossible for a continuous graph to get from this point to this point without passing through this horizontal line. There's no way for me to get from here to here without crossing this line. If the function's continuous, this only applies for continuous functions. Now, where do we care about this? Say I've got some continuous function and I know it's positive here at A. And I know it's negative over here at B. I know the function's continuous and I know it has to go from positive to negative. That means there has to exist someplace in here. I don't know where, but at least one value where it crosses through 0. Like maybe it does a bunch, I don't know. But there's got to exist at least one spot where it crosses 0. Otherwise, how's it going to get from here to here? It's continuous, it can't jump. No jumps are allowed. That's where we use the intermediate value theorem. It's saying we know that there exists a root of our function, a 0 of the function, someplace in this interval. And then later we'll use Newton's method to narrow down on that. So here, I want to prove that this guy has a 0 someplace in that interval. First, I would note f is continuous. It's a polynomial. All polynomials are continuous. I would check f of 0. That's going to be 0, 0, 0, 1. That's positive. F of 1. 1 minus 1, 0 minus 3. That's minus 3 plus 1. That's negative 2. That's a negative number. The only way a function can go from positive to negative is it's got to cross through 0. So then we would say by the intermediate value theorem, there exists a C in the interval 0 to 1 such that f of C must equal 0. So this would be my write-up. I would have everything you see here is required. I would have to write all of that. Now, that doesn't tell me where that value of C is. I have no idea. None. There might be a bunch of them. There could be 100 of them. I know there's not because it's only a third degree polynomial. It can only have at most 3 roots. But I know one of them lives in between here and here. Okay, that's a good place to stop.